Okay, so in this lecture, we are going to discuss about the symmetric group. About the symmetric. Okay, so let us start with the very basic definition of what a symmetric group is. Okay, so let A be a set. Okay, let A be a set, preferably non-empty. Non-empty. Then we define the set SA to be the set of all bijections. Bijections on A. Okay, into A. Clear? So that is, this is defined as the set of all mappings from A to A such that sigma is a bijection. Such that sigma is a bijection. Clear? Okay. Now, suppose we define block n to be the set of natural numbers till n. Okay. Then obviously by the same definition we can form a set of all bijections of these elements. We denote that set as Sn. Okay. So Sn is the set of all bijections on block M into block M, right? Such that sigma is bijection. Okay. So sigma is a bijection. That means sigma takes an element I and sends it to a unique element J, right? Because sigma is 1 1 and sigma is onto as well. So for every element J, we will get such an I, right? Where obviously I and J both are from block N. So this J must be unique for each I, right? Provided a sigma, because this is a 1 1 map. Clear? And also, for every element in block N has a unique pre-image, right? So that is, so if you draw, suppose like this, say you have the elements 1 2 3 4 here, you have the elements 1 2 3 4 here, we are choosing N to be 4. Then there is a mapping which such that every element in this set has a pre-image here and every image is unique. So suppose we send 1 to 2, 2 to 1, 3 to 4 and 4 to 3. Then this gives you an element sigma, suppose in Sn, S4, right? Now obviously whatever I said just now, that has a very trivial implication, that is sigma rearranges the elements in block. So what I basically mean by this is, so suppose you write block n as 1 2 3 4, block 4, let's say block 4, okay, as 1 2 3 4, and you consider sigma from S4 such that sigma maps 1 to 2, 2 to 3, 3 to 4 and 4 to 1, right? Then if you consider the image of block 4 under sigma, then that is nothing but 2 3 4 and 1, right? So this is nothing but, so obviously we are writing it in the order in which we are getting the elements, but this is nothing but a rearrangement of block 4 or rearrangement of this, right? We are not considering at this moment this as a set, because in set we don't need to define an order. But the way we are wanting to describe it is that if you have the elements listed as 1 2 3 and 4, that is the way how natural numbers are listed, then if you consider the listing of sigma 1 sigma 2 sigma 3 and sigma 4 accordingly, then we will get the new list 2 3 4 1, right? So basically, so you had the elements listed as 1 2 3 4, then you list them as sigma 1 sigma 2 sigma 3, sigma 4. But these are obviously the same elements from 1, 2, 3, 4 arranged as 2, 3, 4, 1. So simply we are getting a rearrangement of the same elements. And such concepts we know are permutations, right? Are permutations. So this is the reason why elements from Sn are also called permutations, because they just rearrange the elements listed inside the set they are acting on. Okay. So sigma is called a permutation. Whatever discussion we are having, we are considering this set Sn. Okay, where n basically resembles the block n set. Clear? Okay. Because obviously in an arbitrary set we cannot speak about permutations as such, because an arbitrary set must be a continuum, right? We can consider the sigma, the set to be the open interval 0, 1, right? We can obviously define bijections from 0, 1 to 0, 1, right? But here we cannot distinctly use the concept of permutations because there are no counting numbers. Got it? So whatever discussion we will be having from now are regarding the set of all bijections of block n. Clear? So that's why the elements in Sn are called permutations. Now obviously from your +2 level you know that if you have n elements, n distinct elements, then the number of possible permutations of n is n factorial. So trivially we can say that if you have the set Sn, then the number of elements in Sn is n factorial, because each element in Sn is nothing but a rearrangement of the elements, or rather I should say a certain permutation of the elements of block n. So there can be n factorial number of permutations, hence n factorial number of elements in Sn, and hence this statement. Clear? Now our goal is to find out a way to denote each element in Sn such that it's typically clear what that element exactly resembles. Okay. So the first notation which we will be talking about is, suppose you consider sigma of Sn such that, rather I should take small examples which will be better to understand. Then I will give you the general concept. We consider S4 again, and we choose an element sigma from S4 such that sigma maps 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Then the way we can represent this as an element is that we list the elements 1, 2, 3, 4 in the first row, and we under each element of the first row we represent their corresponding images. So 1 has the image 2, 2 has the image 3, 3 has the image 4, and 4 has the image 1. So this is one way of representing the elements in S4, or rather I should say in Sn. In Sn, if you this representation 1, 2, 3, so on till n, if you have say I1 here, I2 here, I3 here, and so on till In here, then sigma equal to this, rather I should just wait a minute, let me just write sigma here. Then sigma equal to this means sigma maps I to, sigma maps j to ij for all j equals to 1 to 1. Clear? Okay. So this is one form of denoting the elements inside Sn. Clear? Now our next goal is to enhance our notation of each element in sigma such that it's a little bit simpler, nothing else. Okay. So here comes the concept of a cycle notation. Okay. So what's a cycle notation? So this is the most used notation throughout, when you will be working with symmetric groups or permutation groups. These groups are often also called permutations groups. These Sn groups are also called permutations groups because they're nothing but just collection of permutations of the elements in block n, right? So what is the cycle notation? So again let us consider this same example, that is you have sigma inside S4 such that sigma maps 1 to 2, sigma maps 2 to 3, sigma maps 3 to 4, and sigma maps 4 to. Then we can denote this permutation not like this but like this as well. 1, 2, 3, 4. Well, this notation basically means that, let me just change the color to denote this, that 1 is being sent to 2, 2 is being sent to 3, 3 is being sent to 4, and 4 is being sent to, okay. And obviously this resembles a, a loop like structure. So we call this a cycle decomposition. I mean a cycle notation. So on a general basis, this notation, if you have I1, I2, I3, so on till In in Sn, suppose we denote this as sigma, then sigma just maps Ik to Ik plus 1 for all I is equals to 1 to n minus 1, and it maps Ik to, or like this, it maps In back to I. Clear? Got it? So any permutation can be represented in this cycle form. Any permutation you have can be represented in this cycle form. So let me just give a quick example of it. Okay. So suppose you have this permutation. Say sigma sends, say a 1, 2, 3, 4. So suppose it's just 1 to 2, 2 to 1. Then you have 3 to 4 and 4 to 3. Okay. Suppose you have this permutation. Now, how can you come up with a cycle notation of it? So the basic algorithm which is given, it starts, first start with the first element you have in the first row. So you have 1. Denote where 1 goes. 1 goes to 2. So start with 1. We have a 1 going to 2. Clear? Now 2 comes back to 1. So a complete cycle is achieved here. So just close the bracket. Now come up with one more cycle. Obviously, because this everything about this cycle is done, right? Now you have 3 here. So 3 goes to 4. So just start with 3. 3 goes to 4. 4 comes back to 3. So this cycle is also done. So this is the given cycle decomposition, cycle notation, right? Now, so this is basically, this seems like a multiplication, but basically this is a composition. This is a composition because see, Sn, Sn. So it's a collection of functions, right? It's a collection of functions. We say that Sn forms a group under composition. Sn forms a group under composition. And this is pretty easy to notice. Reason being key, if you have two mappings, F and G from Sn, then their composition is also a bijection. And the domain and range remain same, right? Because F has the same domain and range, block n, block n. And G has also the domain as block n, range as block n. So obviously their composition will also have the domain as block n and the range as block n. And it's typically bijective from the fact because F and G are both bijective. So so F composition G is also an element from Sn. This is pretty easy to notice. And inverse mapping also will obviously exist because whatever you are doing in a permutation, if you just step backward, you will get the inverse mapping, right? Let me say sigma sends, let me consider a one example. Okay, so suppose this is the example. So sigma sends 1 to 2, 2 to 1, 3 to 4 and 4 to 3. Suppose you form the mapping where sigma sends, so 1 is sent to 2, so we send 2 to 1, 2 to 1. Let me take a more trivial example because this will be a bit similar to notice. Let us consider this example where sigma sends 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay. Suppose I consider this mapping. So you have 1, 2, 3, 4. So 1 is sent to 2, we send 2 to 1. 2 is sent to 3, we send 3 to 2. Right? 4 is sent to 3 is sent to 4, so we send 4 to 3. And 1 and you have 4 is sent to 1, so we send 1 to 4. Right? This is the permutation you have. Now suppose you compose these two mappings. So now this will also help us understand how multiplication of these elements work, or to be speaking specifically, how the composition of two mappings work in this case. So the other mapping you have is 1, 2, 3, 4, 4, 1, 2, 3. Now we know that sigma 1 composed with sigma 2 of some element is nothing but sigma 1 times sigma 2 of that element, right? So this permutation represents sigma 2 and this permutation represents sigma 1. So what is sigma 2 of 1? So obviously we will start from the right side because the inclusion comes from the right side, right? So we start with the first element from the right side, which is 1. So we see that sigma 2 of 1 is 4. Sigma 2 of 1 is 4. So if sigma 2 of 1 is 4, then we achieve what we will be doing in sigma 1 of 4, right? Because see, sigma 1 composed with sigma 2 of 1. So this is nothing but sigma 1 of sigma 2 of 1. Now sigma 2 of 1 is 4, right? Therefore, this is nothing but sigma 1 of 4. So where does sigma 1 of 4 goes? So 4 goes to 1. So sigma 1 of 4 is nothing but 1. Is it clear? Similarly, now we can obviously enhance on the multiplication, right? We just need to see corresponding elements on the right permutation, and then we want to see what the image goes in the left permutation, right? So now we have the element 2. So 2 goes to 1 here. So the image of 2 is 1 in the right permutation. So we want to check where 1 goes in the left permutation. So in the left permutation, 1 goes to 2. That means 2 will go to 2, right? So we have achieved that sigma 1 composed with sigma 2 of 1 is 1. Now we achieved sigma 1 composed of sigma 2 of 2 is 2. Similarly, we will get that of 3 is 3 and that of 4 is 4. So it's obviously an inverse element. And obviously this inverse is also a bijection from block n to block n. So it's obviously uh, inside the set Sn only. So it's obviously a group. Sn is obviously a group. Okay, let me come up with another example as well. Suppose we have these two permutations. So how to multiply two permutations, or rather how to compose two bijective mappings in this case. So 1, 2, 3, 4, 5, 6, say 2, 6, 5, 3, 1, 4. And here you have 1, 2, 3, 4, 5, 6. Here you have, let's say 6, 3, 2, 1, 4, 5. Clear? So obviously, what we will do is, first let us just list the elements in the first row. 6. Now let us start with the calculation. Right? So obviously the first element we will be speaking about is where does 1 goes. Right? So here we will start from the right. So 1 goes to 6 here. Then we will be noticing where 6 goes to in the left permutation. 6 goes to 4 here. Hence eventually 1 goes to 4. Right? 2 goes to 3 here and 3 goes to 5 here. So 2 goes to 3 here and 3 goes to 5 here. So 2 goes to 5 here. 3 goes to 2 here and 2 goes to 6 here. So 3 goes to 6. 4 goes to 1 and 1 goes to 2. So 4 goes to 2. 5 goes to 4 and here 4 goes to 3. So 5 goes to 3. And 6 goes to 5 here and 5 goes to 1 here. So 6 goes to 1. So this is the permutation you will be getting. Now the exercise you might be taking place, you can just come up with this result using the bijective notation. That is, if you consider this permutation to be sigma 1 and this permutation to be sigma 2, then just find out all possible elements of sigma 1 composed with sigma 2. So that is, what is sigma 1 composed of sigma 2 of 1, sigma 1 composed of sigma 2 of 2, and so on. Right? We will come up with this same result. Got it? Now how can we construct a cycle notation of this? We will follow the same algorithm as we spoke about. So we start with the element 1. So 1 goes to 4, so we write 4. Then you have 4 goes to 2, so we write 2. Then we have 2 goes to 5, so we write 5. Then we have 5 goes to 3, so we write 3. We get 3 goes to 6, so we write 6. And 6 obviously comes back to 1. So this is the cycle notation. Right? Just start with one element and keep writing the element to which it goes on the right side until you reach an element which comes back to the starting element. Right? So we start with 1 obviously. I think it should be clear right now. So you start with 1. We find that 1 goes to 4. So we write 4 here. Then we find that 4 goes to 2. So we write 2 here next to 4. Then we have 2. So 4 goes to 2, right? Now we need to check where 2 goes, right? So 2 goes to 5 here. So we write 5 next to 2. 5 goes to 3. So we write 3 next to 5. And 3 goes to 6. So we write 6 next to 3. Now 6 comes back to 1. So this is the end of the cycle. That's the exact algorithm. I'm not writing the algorithm in the form of steps because now I think it's very easy to understand via examples. Clear? So obviously any permutation you have, you can break it into a cycle format. Obviously, if the permutation is in the form that it can have obviously distinct cycles, as we had just seen in the previous example, right? If you have a permutation, let's say 1, 2, 3, 4, 5, 6. Let's say 1 goes to 3, 2 goes to 6, 3 goes to 4, 4 goes to 1, 5 goes to, let's say, 2, and so 3, 6, 4, 1, 2, 6 goes to 5. Now what is the cycle equation? So we start with 1, yeah, 1 goes to 3, 3 goes to 4, and we see 4 goes to 1. So that's the end of the first cycle. Come to the next cycle. So what are the element left after the last mapped here? So we have 4, right? So we will start with 5 now. So we have 5, so 5 goes to 2, 5 goes to 2, 2 goes to 6, so 2 goes to 6, and 6 comes back to 5. So that's your exact cycle notation. Clear? Clear. Okay. One more thing to notice here is that suppose you have the cycle I1, I2, I3 till I. You can obviously shift each of these elements to the left side by once in a cyclic order. So you can, so what I mean to say is that you have 5, 2, 6 here. Considering this one, you have 5 to 6 here. You can write this as 2, 6, 5. You can write this as 6, 5, 2. See, notice a cycle notation can be visualized as a cycle representation in this form. So you have 5, 2, 6, right? So you write 5 here, you write 2 here, you write 6 here. So 5 goes to 2, 2 goes to 6, 6 goes to 5. So if you rotate it in any way in the clockwise direction, you will get the same permutation, right? So if you just shift it, suppose you rotate it, so you get 6 here, you get 5 here, and you get 2 here. But still the notation is exactly same. So 6 goes to 5, 5 goes to 2, and 2 goes to 6. 6 goes to 5, 5 goes to 2, and 2 goes to 6. Clear? So you can write this as 6, 5, 2. Then if you rotate it once more in the clockwise direction, you will get 2 goes to 6, 6 goes to 5, and 5 goes to 2. So you have 6, 2, 6, 5. Clear? So on a general basis, you can just shift this by one element to the left, right? You write this as I2, I3 till IN, I1. And you can also write this as some I3, I4 till IN, I1 and I2. Clear? Got it? Okay. Now how can we compute the powers of a cycle notation? That is also very easy to notice. Let us first start with an example. So suppose you have this notation, say 1, 2, 3. Okay. Sigma equals to 1, 2, 3. So if I visualize this in the cyclic notation, so you have 1, 2, 3. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. Now what is sigma squared? So notice that sigma squared is nothing but skipping each element in between, right? Because so just notice like this. So you have 1, 2, 3 times 1, 2, 3. So 1 goes to 2 here and 2 goes to 3, right? So 1 is getting directly mapped to 3. Similarly, you will notice 3 is getting mapped to 2 and 2 is getting mapped to 1, right? So sigma squared is nothing but 1 goes to 3, right? So 1 goes to 3, 3 goes to 2, and 2 comes back to 1. Correct? So cyclic notation helps you visualize how powers go. So if you have sigma cubed, then you will have to skip two corresponding elements, right? Let's come up with an example. Suppose you have this cycle 1, 2, 3, 4, 5, 6, and 7. Okay, this cycle, right? So obviously, so this means 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes to 7, and 7 goes to 1. So you have this cycle 1, 2, 3, 4, 5, 6, 7. This exact cycle. Now suppose you denote this as sigma. Then what is sigma squared? So sigma squared is nothing but 1 is getting mapped to 3, 2 getting mapped to 4, 3 getting mapped to 5, 4 getting mapped to 6, 5 getting mapped to 7, and 6 getting mapped to 1. Now if you want to find sigma cube, so sigma cube is, so now if you want to find sigma cube, so obviously you will be now missing two elements in between. So 1 goes to 4, 2 goes to 5, 3 goes to 6, and so on, right? So sigma, so if you have this element, sigma equals to I1, I2, I3, and so on. till ik. Then sigma to the power r, what does it basically do? It maps I1 to I1 plus r. And obviously if you give the notation where I1 goes, so recursively you can give the notation of every other element. So I2 will go to I2 plus r, I3 will go to I3 plus r, and these notations will obviously work modulo n, right? Because after nth element you will be coming back to the elements 1, 2, 3, 4, right? What I'm trying to say is that consider this example. So suppose you name this by I1, name this by I2, and name this by I3. So how does sigma squared work? So sigma squared by our notation, it sends I1 to I1 plus 2. So it sends I1 to I3, and that is obviously happening. One is going to 3. So I am saying that I2 is mapped to I2 plus 2. So what is I2 plus 2? So that is equal to basically I4, right? But we have only 3 elements here. Number of elements inside the cycle is 3. So 4 is equal to I1 under modulo 3. And obviously that is only happening because 2 is coming back to I2 is going back to I1. Clear? That is what I am speaking about. Clear? Okay. Got it? Now let sigma be in Sn such that sigma is a cycle consisting of k elements. Okay, sigma is k elements. That is, sigma is of the form, let's say I1, I2 till ik. Then length of the cycle sigma is k. Okay, so the number of elements in a cycle is defined as the length of the cycle. Okay, and such a cycle called a k cycle. Such a cycle is called a k cycle. Now consider this example. Suppose you have a 3 cycle, which is obviously we consider the obvious example 1, 2, 3. Observe that to bring 1 back to 1, 2 back to 2, and 3 back to 3. So 1 can be brought back to 1 if you have a complete cycle, right? So you have 1, 2, 3. So if you have a complete cycle, you will get 1 to 1, 2 to 2, and 3 to 3. And obviously you can think of this as in any arbitrary k cycle, right? If you have a complete cycle, you will come back to the element you started with. And what is the only possible way to form a complete cycle? If you skip all the elements in between, and that is only possible if you take that cycle to the power of its length, right? So if sigma is a k cycle, then the least positive integer such that sigma to the least positive integer k such that sigma to the power k is equals to 1 is nothing but the length of its cycle. Rather, I should suppose sigma is a cycle. Then the least positive integer k such that sigma to the power k equal to 1 is nothing but its length. Clear? And since it's the least positive integer to happen, so therefore if sigma is a k cycle, then order of sigma is equal to k. Clear? I hope this is pretty clear. Got it? Okay. Okay. Now sigma and sigma dash are said to be, sigma and sigma dash are said to be disjoint cycles. If they are cycles individually and have no element in common, clear? For example, just just take the cycle, say 1 2 3 4. This is obviously a so sigma, suppose this is sigma dash, then sigma and sigma dash are disjoint cycles because they are cycles and they have no element in common. Now also this is pretty evident that if you have two disjoint cycles, sigma and sigma dash, then they will obviously commute, right? Disjoint cycles commute. What is the reason behind that? Reason, suppose you have two disjoint cycles. Say you have I1, I2 till Ik is one disjoint cycle. So is one cycle, and then you have here say J1, J2 till some JR, B2 disjoint cycles. Such that, okay, yeah. Now since they are disjoint cycles, so obviously whatever permutation is going on here has no relation with any permutation going on here, right? So the multiplication is basically independent of each of these cycles. Whatever permutation you have here, if it is independent of whatever permutation is having here, then there is no relation in between the elements and their arrangements of these both cycles, right? So multiplicating them will obviously commute, because in whichever order you multiply, whether you do this first or you do this first, will have no difference, because in case of two permutations being multiplied, okay, in case of two multiplications being multiplied, they do not commute. The reason being, if you have some element here I1 which is getting mapped to say I2, then if I2 is getting mapped to some different element here I3, then you will having be so from the right hand side if you start, then you will be having I1 going to I3, right? Now if you just inverse, suppose you have I1 going to I2 on the left and I2 going to I3 on the right. But in this case what happens? Suppose you have say I1 going to I4 here, then I1 goes to I4 here, but so basically I think you people have understood that this multiplication will be different, right? Let me just consider an example to make this understand, a more specific example. Okay. Suppose you have say 1 2 3, okay, so let's say 1 goes to 2, 2 goes to 3 and 3 goes to 2, sorry 3 goes to 1, and you have 1 2 3. Here you have, let's say 1 goes to 3, 3 goes to 2, 3 goes to 2 and 2 goes to 2. So what does the product will give? So you have 1 going to 3 on the right and 3 goes to 1 on the left. 3 goes to 2 on the left, right? So 1 goes to 2. Clear? 1 goes to 3 here and 3 goes to 2 here. Or am I doing something wrong? Okay, 1 goes to 3 here and 3 goes to 1 here, correct? Yeah, 3 goes to 1. Okay. No, I don't think this will make a good example as well. No, this won't make a good example. Let me think of something else. Yeah, let us start with say 1 2 3 only. If 1 goes to 2, 2 goes to 3 and 3 goes to 1. And let's suppose we have here 1 2 3 such that 1 goes to 2, 2 goes to 1 and 3 goes to 3. Yeah, let's try this out. So from the left what happens? So 1 goes to 2 and here 2 goes to 3. So 1 goes to 3, right? So from the here we have 2 goes to 1, here 1 goes to 2. So 2 goes to 2 and you have 3 goes to 3 and here 3 goes to 1. So 3 goes to 1. What happens if you take 1 2 3 and 2 1 3 here? You have 1 2 3 and 2 3 1 here. Okay. So here 1 goes to 2, 1 goes to 2 and here 2 goes to 1. So 1 goes to 1. Here you have 2 goes to 3, here you have 3 goes to 3. So 2 goes to 3 and here you have 3 goes to 1 and here 1 goes to 2. So 3 goes to 2. And obviously these two are not same, right? So they're not commutating. And why are they not commutating? Because these two permutations are interrelated, having same elements in them. And at least one element same in them. Getting my point? So hence, if you had, suppose Now let us think of this, or think of it like this. Suppose you had the second permutation as, say, 1 goes to 1, 2 goes to 2, and 3 goes to 3, for example. Okay. Or let us just think of it like this. If there was no permutation common in between them, then they would have no relation in between them. So multiplying them from either side will cause no difference. That is what I am trying to speak. And that is the reason why disjoint cycles will commute. Because if you multiply two disjoint cycles, I1, I2 till Ik, and J1, J2 till Jr, then we do not have to notice anything about the images on the right cycle of what happens to them on the left cycle, because they will obviously have no element in common. Clear? So multiplying them from the left or right doesn't make a difference. So this must be same as J1, J2 till Jr, and here you have I1, I2 till I. So disjoint cycles come. Clear? Okay. Now suppose you have a permutation sigma from Sn such that sigma can be written as tau 1, tau 2 till tau k, such that each tau I is a disjoint cycle. Okay. So sigma is a product of disjoint cycles. Then sigma to the power r is obviously tau 1, tau 2 till tau k to the power r. And we know when such an element you have a product of certain elements which commute with each other, because since each tau I is a disjoint cycle, therefore every tau, so tau I and tau j in between these elements will obviously commute, right? So every element tau 1, tau 2 till tau k will commute with each other. So obviously when you have the product of them, so it's of the form tau 1. Suppose we consider the square of them first. Okay, then you will be understanding the concept. Suppose you have sigma squared. So this is tau 1, tau 2, tau 3 till tau k times tau 1, tau 2 till tau k. But using commutativity, you can obviously bring tau 1 beside tau 1, obviously using commutativity. You can associate these two elements, commute them, then you can associate tau k minus 1 with tau 1 and then again commute them. So you will get tau 1 squared, tau 2 squared till tau k squared, right? On a similar notation by induction, you will obviously achieve that sigma to the power r will be nothing but tau 1 to the power r, tau 2 to the power r till tau k to the power r. Clear? Got it? Now, our question is, what is the order of sigma? What is the order of sigma? That is, we want to find the order of product of disjoint cycles. Product of disjoint cycles. Clear? Now obviously, if order of sigma is equals to d, then tau 1 to the power d, tau 2 to the power d, and so on, tau k to the power d is equals to 1, right? But since each tau I are disjoint, therefore tau I to the power d must be identity for all I is equals to 1 to n, 1 to k, right? Because obviously by the same thing which we had just discussed previously, that since tau I and tau j have no relation with each other, so their product is basically nothing, because their product is independent of them mixing together. Their product is just depending on each tau I and tau j. So for the product to be identity, both of them individually needs to be the identity, right? So tau I to the power d must be 1. But we know that the order of tau I is the length of it. So order of tau I divides d, right? Order of tau I divides d. Now let length of tau I be ai. Then ai divides d for all I equals to 1 to n. Then that implies the LCM of these ai's I equal to 1 to n, 1 to k, right? 1 to k. divides D by the properties of LCM. By the properties of LCM. And obviously we know that the LCM of these elements is the least such number which will produce this effect. That's so if LCM of each of these AIs I equals to 1 to K is considered to be L, then obviously sigma to the power L must be 1, because sigma to the power L is nothing but tau 1 to the power L till tau K to the power L. And since AI divides L, therefore L can be written as some AI times let's say SI. So tau I to the power L is nothing but tau I to the power AI whole to the power SI, and tau I to the power AI is 1. So this becomes 1. So that means sigma L becomes 1, and L is the least such element to happen so. Right? So this implies therefore order of sigma must be equal to L. That is D must be equal to L. Nothing else. Clear? Therefore, order of a product of disjoint cycles is the LCM of the length of each cycle. Clear? So if you have a product of disjoint cycles, then you can obviously find the order of that permutation. Clear? Okay. The next important cycle which we have inside a permutation is the two cycles. Okay. So definition: a two cycle, that is a cycle of length 2, is called a transposition. Okay. Now we can obviously decompose each permutation from Sn into cycles, right? That's called the cycle decomposition. Each permutation can be written as a product of cycles. Obviously not necessarily distinct. They need not be distinct. Okay. But we can obviously write them into product of cycles. Okay. So every permutation can be written as a product of cycles. If you specifically notice that every permutation can be indeed written as a product of disjoint cycles, to be very precise, because any permutation you take, say 1, 2, 3, 4, 5, here you have 5, 4, 1, 3, 2, then what is the cycle? So you start with 1, right? So 1 goes to 5, 5 goes to 2, 2 goes to 4. This becomes, suppose we write this to be 1, say this is 1. Okay, this is say 4, then this becomes, so you start with 1, so 1 goes to 5, 5 goes to 2, 2 comes back to 1, and 3 goes to 4, 4 comes. So this is a disjoint cycle. So this algorithm basically gives you disjoint cycles. So we can write that it's a product of disjoint cycles, because the algorithm which we follow to decompose the permutation into the cycle notation, that indeed gives you disjoint cycles, because we end a certain cycle, the point we get as a complete reversing of the elements, right? We end the cycle as soon as we reach that element 2 which comes back to the starting length, right? We end the cycle there. So obviously there is no chance that two cycles will have the same number of elements, because if it would have been, then this, suppose some of the element in this first cycle has an image to be 3, then image would have been, then that 3 would have been in the same cycle as the left cycle. Yeah, that is the concept. So the algorithm which we follow actually gives you gives you a decomposition of any permutation into disjoint cycles. So obviously every permutation can be written as a product of disjoint cycles. Now every cycle can be decomposed into a product of transpositions. And this is pretty trivially noticed, because if you have this cycle, let's say A1, A2, A3 till AK, this can be written as A1 AK times A1 AK minus 1, so on till A1 A2, and this will do. Clear? Clear? You can obviously just consider the right hand part and keep multiplying. You will notice that you will be coming back to this cycle. This is a pretty easy example to understand. Clear? So every cycle can be decomposed into product of transposition, not necessarily distinct. Not necessarily distinct. Clear? Or disjoint, I should say. Got it? Now, since every cycle can be decomposed into two cycles, therefore we can say that the permutation group Sn can be generated using two cycles, right? So we can write this as generated by the set T, such that T is the set of two cycles ij, such that 1 less than equal to I less than j less than equal to 10. Clear? Got it? Now we have a very important concept related to two cycles, that is, let me just give a brief introduction to it. That is, a permutation is said to be an odd permutation, if it can be decomposed into odd number of transpositions. Right? Now, and so if you have a definition of an even permutation, that can be decomposed into even number of transpositions. That is it. Clear? Got it? Now notice one thing. If you consider this example, so this is a k cycle. And what are the number of transpositions you have here? So you have k minus 1 number of transpositions. Therefore, if you have a k cycle, then you can decompose this into k minus 1 transpositions. Right? Therefore, if you have an odd cycle means k is odd. That is, the length of the cycle is odd. Then an odd cycle gives you an even permutation. Because if the length of the cycle is odd, then it can be decomposed into even number of transpositions. Because if k is odd, then k minus 1 is even, right? So if you have an odd length cycle, then that can be decomposed into even number of transpositions. So it becomes an even permutation. Clear? Similarly, if you have an even cycle, that is, the length of the cycle is even, then you will get an odd permutation. Clear? The set of all even permutations is actually which is more important. Clear? One sec. Okay. So let's come up with the next concept. So we are gonna now discuss about this parity of permutation, that is, odd permutations and even permutations. Okay. So the parity of permutations. Okay. So to have a detailed explanation about the parity of permutations, we need some prerequisites. So let's just start with those. Okay. So our target is to show that the parity of a permutation is unique, right? Because there are multiple ways to decompose a cycle into product of transpositions. The way I showed is not the unique one. You can decompose a cycle into multiple number of transpositions, but our goal is that whichever way you decompose a cycle into transpositions, the parity of the permutation is always unique. That is, if it's even, then it's always even. Clear? So for that we need a different sort of definition to odd and even permutations. Let's start with that. Okay. Now suppose x1, x2 till xn be independent variables. So these are certain variables, and define a polynomial delta as product of elements as xi minus xj, right? So if I give a quick example, suppose you have n equals to 4, then pi is nothing but x1 minus x2, x1 minus x3, x1 minus x4 times x2 minus x3, x2 minus x4, x3 minus x4. Clear? Now let sigma belong to Sn such that sigma operated on delta just permutes the variables xi's such that on a similar way as it would permute their indices. That is sigma delta is nothing but product of 1 less than equal to I less than j less than equal to n of x of sigma I minus x of sigma j. Now obviously I and j are from block n, which is pretty trivial to notice that each I and j are from block n, and so sigma just permutes. So sigma is a permutation inside Sn, right? So sigma will permute the elements ij. So the elements xi xj gets so xi is mapped to x sigma and xj is mapped to x sigma. So this is a way in which we can think of this. Clear? So let's consider an example again. So we will be discussing throughout these examples. Okay, n equal to 4 and pi equal to this. Okay, so suppose sigma is equals to 1, 2, 3, 4. Then what is sigma of delta? So 1 goes to 2, right? So the first element becomes x2 minus x3. The second element becomes x3 minus x4. Third element becomes x. So you have x1 goes to x3, right? So it becomes x2 minus x4. This becomes x2 minus x1. Then you have x2 minus x3. So that goes to, so 2 goes to 3. So this becomes x3 minus x4. And this becomes x3 minus x1. And the last element, so 3 goes to 4. So this becomes x4. And 4 goes to 1. So this becomes x1. Got it? Clear? Okay. Now the way delta is defined, it contains only one element or only one factor xi minus xj for all I less than j, right? You have only one factor of the form x1 minus x2, right? You have only one factor of the form x1 minus x2. You have only one factor of the form x2 minus x3. Clear? So delta has only one factor of the form xi minus xj. Clear? Therefore, sigma operated on delta can have only one factor of the form. So only one factor of the form xi minus xj or xj minus xi. So you had one factor of the form x1 minus x2 in delta. So sigma delta has only one factor of the form x2 minus x1, and x2 minus x1 is nothing but xj minus xi form, right? Because the indices are still in the block n only, so the indices won't change. So if you have one element of the form xi minus xj in delta, you will obviously have one element of the form xj minus xi or xi minus xj itself from sigma delta. Clear? And no element of the form xi minus xi, right? Because suppose if you have two elements of the form xi minus xj in sigma delta, then that doesn't remain so sigma doesn't remain a 1-1 mapping anymore, right? And the same in this case also. Okay. Suppose let's say xi minus xj, this goes to xk minus xl, and let's say xs minus xt also goes to xk minus xl. So that means sigma I equal to k and sigma s is also equal to k, but I is not equal to s. But that is not possible because this is a 1-1 mapping, right? That is the reason why this happens, and that is the reason why this happens. Got it? Okay. Now, if sigma delta has a factor of the form xj minus xi, if sigma delta has a factor of the form xj minus xi such that I is less than j, then we can say it has a factor of the form minus of xi minus xj such that I is less than j. Clear? Now, so this is basically a change in sign inside the permutation sigma delta from delta, right? One second. Right? So this obviously a change in sign from delta to sigma delta, which marks a change in sign from delta to sigma delta, because delta had the factor xi minus xj and sigma delta has the factor minus of xi minus xj, and such factors are uniquely present. So this marks a change in sign, obviously. Okay. So if I collect all possible change in signs, collecting all possible changes in sign from delta to sigma delta, it's obvious that sigma delta is nothing but plus minus delta. Clear? Got it? Sigma delta is nothing but plus minus delta. And this happens for all sigmas in S. Because sigma was chosen arbitrarily, so this is obviously possible for all such permutations. So we define epsilon to be the sign of sigma, where for all permutation sigma in Sn, epsilon of sigma is equal to plus 1 if sigma delta is equals to delta and is equals to minus 1 if sigma delta is equal to minus delta. Clear? So from the example, you can obviously find out. So this you can consider this as an exercise. Let n be equal to 4, sigma b is equals to 1, 2, 3, 4. Then find out that what is the value of epsilon of sigma. It's minus 1. You can obviously check it out. Clear? Got it? Okay. So this epsilon is called the sign of sigma. Okay. Definition: sigma is called an even permutation. Sigma is called an even permutation if the sign of sigma is 1, and called an odd permutation if the sign of sigma is minus. Clear? Clear? Okay. Got it? The next thing we claim is that this epsilon, so since we can obviously denote epsilon as a mapping, so we claim that epsilon is a homomorphism from Sn to the set plus minus 1, because it can only consider the elements plus minus 1. Okay. So proposition: the map epsilon from Sn to the set plus minus 1 is a homomorphism. Okay, and plus minus 1 typically is the multiplicative form of the additive cyclic group Z. Clear? Clear? Okay. So let's come to the explanation of this. This explanation is also pretty easy to notice because you consider tau sigma of delta. So this is nothing but from the definition, it's pi of 1 less than equal to I less than j less than equal to n of x of tau sigma of I minus x of tau sigma of j. Right? Now suppose sigma delta has k factors of the form xj minus xi. Okay. Suppose sigma delta has k factors of the form xj minus xi, where I is less than j. Clear? Therefore, the sign of sigma is minus 1 to the power k. Clear? And tau of sigma delta has exactly k factors of the form x tau of j minus x tau of I. Right? Where I is less than j. Right? Now if I interchange the order of these terms, okay, then we get again a sign change of minus 1 to the power k. Interchanging the order of these terms, we get a sign change of minus 1 to the power k again. So that means if I change the order of these terms, then I can map the this delta with respect to tau, irrespective of what the sign change with respect to sigma was. Right? Irrespective of what the sign change with respect to sigma was. So that is we can, if we tend to write this as sigma tau of p minus x of tau of q, where p is less than q. But this would obviously imply that tau sigma of delta is the sign of sigma times this x tau p minus x tau q, because we have changed the order of the elements here, right? Previously, when we had acted upon this polynomial with sigma, then we had got a sign of minus 1 to the power k, and then we acted on that same polynomial with respect to tau. We again changed the order of tau such that the element I on the left hand side is less than the element j on the right hand side, which is we represent as p and q. So if we want to get this condition of p less than q, and to get that condition, we tend to change all those k factors, the sign of all those k factors, which had given us the sign of minus 1 to the power k. So we get another sign change of minus 1 to the power k again, but that nullifies whatever we had, right? Because minus 1 to the power k times minus 1 to the power k is nothing but 1. So acting on delta with respect to tau is analogous to acting on delta without sigma, without the presence of sigma. So this is completely independent of whatever we do, whatever we had done with sigma, right? So obviously the sign change of sigma will simply come outside, right? And on analogous steps, so this becomes epsilon sigma times epsilon tau of delta, right? But that means the sign of epsilon tau sigma is nothing but epsilon sigma times epsilon tau. Obviously epsilon, the images under the mapping epsilon will commute because they are the elements plus and minus 1 under the multiplicative group plus minus 1, so they obviously commute. So this is nothing but epsilon tau times epsilon sigma. Therefore epsilon is a homomorphism. Epsilon is a homomorphism. Clear? Got it? Clear? Now the kernel of this homomorphism is what we define as the alternating group. Okay. Definition: kernel of, or rather I should write it like this, the alternating group of degree n, denoted as an, is the kernel of the homomorphism, Clear? Then, okay, therefore, by the first isomorphism theorem, Sn mod An is isomorphic to the image of Sn under epsilon, right? But the way epsilon was designed, we had the range of epsilon to be plus minus 1, and so that was the exact codomain of the set, right? So epsilon is indeed a surjective mapping. Epsilon is indeed a surjective mapping. To ensure that, why I am telling epsilon to be a surjective mapping, because we claim that with respect to the element 1 and with respect to the element minus 1, we will get elements from Sn such that their sign is plus 1 and their sign is minus 1 respectively. Let us first claim that. Okay. To claim that, we need to understand how this sign change works in case of transpositions. Okay. Suppose we consider the transposition 1. Okay. Then notice that this permutation, if this is sigma, then sigma causes a change in the element x1 minus x2. Okay. 2. So 1 goes to 2, right? So this will become x2 minus x1, right? Clear? So sigma only inverse exactly this one element, x2 minus x1. Clear? Because the other element has no sign change. The other element will have no sign change. Because in every other case, if you have the element x2 minus x3, see those factors which have 1 and 2 not in them, those factors have nothing to do, right? But if you have the element x2 minus x3, then 2 goes back to 1, so this becomes x1 minus x3. So there is no sign change. The only sign change possible is when the indices have 2 and 1 both, which has 2 and 1 both, and that is this very factor. So therefore the epsilon of sigma is minus 1, right? Now on a similar basis, we check what an arbitrary transposition can do. What is the sign of an arbitrary transposition? Okay. So suppose Ij is a transposition. Ij is a transposition. Let lambda be the permutation which interchanges 1 and I. interchanges 1 and I, 2 and j, and leaves all other elements fixed. Okay, so lambda is that permutation which just maps 1 to I and maps 2 to j, or rather I should say interchanges 1 to I and 2 to j. So it's a, so lambda is kind of a cycle which maps 1 to I to 1, 2 to j, and j to 2. Clear? And all the other elements are fixed. Therefore ij can be simply written as lambda times 1 2 times lambda, right? Therefore what is epsilon of ij? So since epsilon is a homomorphism, so it's epsilon of lambda, epsilon of 1 2, and epsilon of lambda. Now epsilon is 1 to minus 1, so it's minus 1 times epsilon of lambda whole square. So epsilon of lambda can be 1 and minus 1 only, so this whole square term is positive obviously, so this implies epsilon of ij is minus 1, right? Therefore the transpositions are odd permutations. And if you obviously observe the identity element in sigma, then the identity element in sigma will cause no changes in sign, so its sign will be 1. Therefore that's an even permutation. So with respect to the element 1 we get the permutation, identity permutation, and with respect to minus 1 we can obviously get an odd permutation from the set of permutations which we just showed by example. So transpositions are odd permutations and epsilon is surjective. Now if epsilon is surjective, then obviously since we had Sn mod an to be isomorphic to the epsilon of Sn, so what will be epsilon of Sn? So epsilon of Sn will be plus minus 1, right? So this implies the order of Sn minus an, sorry, the order of Sn mod an is 2, which implies the order of an is half the order of Sn, which is equals to 1/2 of n factorial. Clear? If you carefully notice what elements of an are, so these are the elements sigma in Sn such that the sign of sigma is 1, but those sigmas are called the even permutations. Therefore an is the collection of all even permutations, right? So there exists exactly half the number of permutations, the number of even permutations, right? The number of even permutations. So is it clear? Right. Yeah. So it's surjective because every cycle can be decomposed into transpositions, right? So if every cycle can be decomposed into transposition, you can always get a cycle which can be decomposed into a single transposition. So or obviously, very strictly speaking, we can always get a transposition inside a permutation. So if I get a transposition inside a permutation group, the sign of the transposition will obviously be minus 1. So obviously that exactly means epsilon is surjective, right? Okay. So exactly half the number of permutations. Let me just add this part again because I have this in a horrible handwriting. So therefore there exists half the number of even permutations as Sn. Clear? So other half are the odd permutations. So Sn consists of half even permutations and half odd permutations. That is what I wanted to speak about. Clear? Now An is obviously normal because it's a kernel of a homomorphism. So it's obviously normal. Clear? If you know about the conjugates of a permutation, which I have not yet discussed, but if you know about it, then we should also know that two permutations are conjugates if and only if they have the same cycle type. They have the same cycle type. So therefore, if you consider any element from An, every element of An will have the same cycle type, right? Because they are all even permutations. And we have already known that, if you have a odd number of odd length cycle, then that's an even permutation. So if you consider an element from N, then you will obviously get another element of N of the same cycle type. Same cycle type in the sense you can think of it as the same length. Okay. The most trivial part to think about it is having same length. Okay. Let me just think of any other sort of an example if I can think of it. One sec. Yeah, so basically it is that let me just so same cycle type basically means, let me just give you the basic example or basic definition. Suppose sigma is in Sn such that sigma is product of disjoint cycles of lengths n1, n2, so on till nr. Okay. Then these integers n1, n2, and nr are called the cycle types of sigma. So two permutations are conjugate if they have same cycle type. That is, the lengths are same. Okay. So the other permutations is sigma dash. If it is the product of these joint cycles of the length n1, n2 till nr, such that this happens again, obviously. So they are of the same cycle. That is what I tried to say. Whatever. Clear? Okay. So with respect to the concept of conjugates having the same cycle type, you can also claim that An is normal. But it's trivially normal because it's the kernel of a homomorphism. Is it clear? Is it clear? Now, let us come to something more. Okay. Suppose sigma is in Sn. So that sigma is written as tau 1, tau 2 till tau n, tau k, say, whose where each tau I is a transposition. One more thing let me just make it clear here. When we have the cycle decomposition, we do not write the cycle decomposition, or we do not write the one cycle. Okay, one cycle is a cycle of length 1. So this cycle means 3 is mapped to 3. So we ignore writing the one cycles when we are writing the cycle decomposition of any permutation. So obviously this k can be less than equal to n because we have not written the one cycles. So there obviously is no concept of a transposition from those cycles. So sigma is written as tau 1, tau 2 till tau k, where tau I is the transposition. Then what is epsilon of sigma? Since it's a homomorphism, so it's epsilon times tau 1, epsilon times tau 2, so on till epsilon times tau k. Clear? So this is obviously minus 1 to the power k4, right? Because each transposition gives you a sign change of minus 1, or rather gives you a sign of minus 1. So it's minus 1 to the power k. Thus, epsilon of sigma is 1 if k is even, and is minus 1 if k is odd. But what does k is odd mean? So k is odd means that sigma is the product of odd number of transpositions, and sigma being a product of odd number of transpositions means sigma is an odd permutation, right? Therefore sigma, or I can directly write it as like this, that a k cycle is an odd permutation if and only if it is an even cycle. right? This is what we just spoke about. So so if k is even means sigma is the product of even number of transpositions, and even number of transposition means so even number of transposition means, sorry, let me just go by the definition. So k is odd. K is odd means sigma is the product of even odd number of transpositions. That means it's an odd permutation. But it is an odd permutation if it's an even cycle, because then the epsilon becomes 1, right? Got it? It's an odd permutation because if it's an even cycle, yeah. Is it clear? Clear? Got it? Clear? Okay. Got it? So on a similar notation, we can also say that a permutation sigma is odd if and only if the number of cycles of even length, in it is the cycle decomposition is odd, right? Which we have started with the definition, because this very definition is eventually giving us that very definition which we had started with, that if you had a k cycle, then you have k minus 1 transpositions. So if k is odd, then you have even number of transpositions, so it's an even cycle, right? So a k cycle is an odd permutation if and only if it is an even cycle. Clear? Got it? Okay. So let this be up till this much. In the next lecture, we will be speaking about some more important topics. I am trying to bring out a lecture on the dihedral groups. Okay. So meet you guys in the next lecture.